You have written that you began exploring the technical world by playing with Legos. I don't want to talk about Legos right away, but is there a technical world versus any other kind of world as you understood it when you were growing up? What is a technical world?
Well, the world of gadgets, tinkering, constructing things.
And this was the world that you embraced as a young child?
Yeah. It may be difficult to rigorously define it, but I think if you see young children, whether they play with stuffed animals, whether they read books, or whether they want to work with tools, the children are expressing something about their preferences.
And your preference was clearly grab the tools, build some stuff, and then build it again.
True.
Mm-hmm. What first made you think that science was a place to express this kind of impulse in the technical world?
Well, I found out what I liked at school, and at school, well, let me start again. I think when you're a child, you don't really know what science is. You don't know what mathematics is. But one aspect is playful exploration. And then another aspect is you take those subjects in high school. And I always liked physics and mathematics the best.
There's plenty of people, particularly at the time that you were growing up, who viewed physics and mathematics as a domain of thought and abstraction, and not necessarily a place where you would build tools to inquire into the nature of matter. Why didn't you take the path of maybe more theoretical physics, and how did you embrace the building of tools, so many of which have been revolutionary in the studying of states of matter?
I actually disagree. I think it was clear for me from the beginning that science has an experimental side, and what actually drew me into science was both my love for mathematics, my love for abstract thinking, but also I love to tinker, to play with things. I had a motorbike and I liked, and I was repairing it and doing some modifications. I had a chemistry set, so I was exploring science on the hands-on side, and I enjoyed it.
And so really from the earliest age, there was a unity of abstract science and experimental work that you've carried with you throughout your career.
That's correct.
Yeah.
Actually, I was quite interested also in a career in mathematics, and I just felt that physics would connect me more with the real world, and the real world also means the possibility to do hands-on work. On the other hand, this interplay between experiment and theory during my career has taken a few turns back and forth. For instance, at the end of my undergraduate studies, I did a purely theoretical master thesis. So at that point, I actually wanted to become a theorist.
Why did you choose that at the end of your undergraduate study?
Because I was fascinated by that. First of all, most of our education is theory-based. In high school, at least at my time, we hardly had any lab classes. So it was all teaching, understanding the concepts. And also at the university, sure, we have the equivalent of junior lab, and so we went through those lab courses, but the far dominant portion of the education is actually more conceptual and theoretical.
What was the first academic setting that you came into where you looked around the lab and saw machines that were really worth tinkering with, that had the capacity to explore questions that you thought were really fascinating?
Probably when I started my PhD. But I mean, it goes back and forth. I think I've been a person who has been talented for both, and who has intuition for both. I remember when I took lab classes and there was some torsion pendulum. I was just fascinated by that. I could play with that. I was experimentally realizing what was in the differential equation. So I really felt I wanted to feel physics, I wanted to see physics, but nevertheless, a couple of years later, I picked a theoretical topic as my master thesis. I think I was always fascinated by the power of describing nature. And when I learned about statistical physics, I found it fascinating that you can make a few assumptions about what atoms do, kind of some probabilistic arguments of entropy, and you can deduce the equation of state of the whole system. So by just very few assumptions or very few things you know, you can deduce a lot, and that fascinated me. So therefore I decided to work on a theoretical subject for my master thesis.
Is it an accident that it seems that one of the patterns in your academic career is that you typically would choose problems and projects that were beyond the capabilities of the lab equipment at your disposal, of the machines that were available at your disposal?
I fully agree. It is the style of my group to push the frontiers of the field. I tell all the students who work with me or who want to work with me, if you want to work with me, you have to be a hardcore experimentalist, because our job is to push the boundary of what is possible. So my lab, my group is extremely focused on doing new things, doing things which currently seem impossible or out of reach, but bring them into reach.
When did you first have the experience of encountering a question that required you to make a brand new tool to investigate that question?
Your question sounds too much black and white. Because tools are new, but maybe not brand new. You have ideas, you see something and modify it. And it sometimes depends on how familiar you are with the detail, whether the modification looks revolutionary or brand new. I always felt what I did was almost the logical next step. But viewed from the outside, it looked to people like quite a bold move.
Well, I'm not trying to, over-characterize the boldness or the inventiveness, but I think there's a classic story in science there where you have a question that you're dying to get to the bottom of, and you really need to invent or modify the existing tool set to enable you to get there. So it requires a number of jobs to get to the
I see an interplay. There's an interplay between technological advances and experimental advances. Suddenly you realize I have a tool, you look for science and you find new science. But sometimes you are interested in solving a burning scientific question, and then you think which tool can help us. So sometimes I have allowed myself or my group to develop tools in search for the right question, just to be sort of ready to attack the question, or there was a question, we developed a tool specific for that purpose. So it sometimes depends. Sometimes your research may be more technological, driven by finding better tools to go deeper into science, and sometimes you are motivated by a scientific question.
You seem to have been drawn to the idea that in spectral analysis of atoms and molecules, the individual signatures can tell you a lot about the states of matter. You stayed there for quite a while.
That's true.
What did you love about that particular domain?
Well, I found it, and I still find it fascinating, that when you look for a spectrum of an atom or molecule, that you can learn all the details about the atomic and molecular structure just looking at the frequencies in the electromagnetic spectrum at which the atoms or molecules resonate. So I was particularly excited about it when I, during my PhD, discovered a new molecule and there was hardly anything known about it. And I had a spectrograph. I looked at the light which was emitted by the molecules, and it were hundreds, if not 1,000 of different spectral lines. And a lot of them were not regular. It didn't make any sense initially. And it took me, I think, about 2 years or so to solve the puzzle. So I had to learn a lot of theory. I had to do a lot of computer simulations. I had stacks of papers of simulated spectra, just trying to find a simulation on the computer which became similar to the experimental one.
And the molecule?
The molecule was helium hydride. It was a molecule consisting of the 2 lightest elements in the universe. So it was a very special molecule. And after 2 years, I had found the code. I'd really deciphered the code of nature, and for the first time I knew what is the size of the molecule, how stiff is the bond between the helium and the hydrogen. So all the basic questions you ask about a molecule, I could answer. I found it extremely fascinating to be able to do that, and it was even more fascinating for me since I worked at an institute which didn't have the tradition of doing that. So almost everything I had to learn by myself, or learn by asking other people, learn by reading the literature. I think it was a very important step in my development as a scientist.
And that was at the Planck Institute?
This was at the Max Planck Institute.
Yeah. What brought you to MIT?
Laser cooling and Dave Pritchard. So that is actually an interesting story. If you allow me to fill in some gaps, we've talked about spectroscopy, which was my PhD work and the work I did during my first postdoctoral appointment, still at the Max Planck Institute. And I've also expressed to you the fascination and also the satisfaction I had in analyzing a brand new molecule. On the other hand, I felt after 3 years as a postdoc, I was sort of at a dead-end street, because this kind of molecular spectroscopy, most of that was done early on, and there were not many molecules left over to do that kind of analysis. And also the frontiers of the field were different. So I felt the molecular spectroscopy I did was neither applied nor fundamental. And I felt if I wanted to make an important contribution to science, technology and knowledge, I should either do something which is clearly applied or which is clearly fundamental. So I was at crossroads. And I decided to work on an applied project, because throughout my studies as an undergraduate student, or also during my PhD, I always wanted to do something more applied. Applied means something which is more directly related to the needs of society or the burning questions which we have to solve as a nation.
What are those burning questions, and what do you sense is a scientist's responsibility in responding to the needs of society?
Well, scientists can respond in many ways, but one of the needs of the society is to protect the environment, to avoid pollution. And I felt as an atomic physicist who understood spectroscopy, there was an opportunity for me to contribute, namely to work on using spectroscopy to monitor combustion. So I went into combustion diagnostics. So I used my knowledge of spectroscopy and applied it not to new and potentially esoteric molecules. I applied it to flames in a Bunsen burner, flames inside a diesel engine. So my goal was, and this is what I picked as my second postdoc, and at that point I intended to make it my career, to use lasers in spectroscopy as a tool for cleaner environment. To make combustion more efficient, to make combustion cleaner.
Monitor the combustion, and by doing so, come up with ways of making it more efficient and getting rid of pollutants and contaminants.
Exactly. So the program was that the program was a combination of theorist and experimentalist. I was the experimentalist who helped to develop new tools of diagnostics. So the idea was that you can measure with high spatial and temporal concentration molecular concentrations. So in the end, that experimentally you can say at what phase of the combustion cycle do pollutants formed, or to figure out how well is the fuel mixed with air and all that, and to measure local temperature fields, to see if the flame front is irregular or if it's regular and all that. And at the same time, we had theorists who used, theoretical chemists, who used models of combustion. And so the hope was, which eventually came true over the last decade or so, that by comparing results of theoretical predictions and comparing that with detailed combustion diagnostics, that you could verify the computer codes and help to develop them. So that ultimately we would wind up with a much better understanding of what limits the efficiency and what causes pollution to occur during combustion.
What did you have to do to modify traditional lasers to make this diagnostic tool a reality?
For a lot of the work you can use commercial lasers, but you either have to adopt the lasers to the special purpose or to do some modifications. And during that year in Heidelberg, I worked with ultraviolet lasers, and one of the, it was probably not an earth-shattering idea, but a nice idea I had is to modify a laser from a single wavelength into a dual wavelength laser. And with that, we had a two-channel capability, which meant we could monitor two chemical species simultaneously. So that was a nice development. It was a fun for myself and for the people around it. We even took out a patent. I think in the end it didn't really have a big practical impact, but that was sort of one example where you want to improve your tools, or you want to really master your tools in order to use them for your scientific purpose.
Those skills really would help you later on in your low temperature work. But before we get to that, how did a laser lead you to MIT?
No, I mentioned laser cooling and Dave Pritchard.
Yeah.
Anyway, so I think we are now at that stage.
Yeah.
So I've just told you what I did before I come to MIT,
right.
namely really applied research. And applied research was also for me to eventually realize some of the thoughts or some of the aspirations I had when I was a student. I wanted to work on something practical. Mm-hmm. I've already mentioned that I had sort of two forces in me. One was the desire to work on something applied to solve practical problems, and the other aspect was my talent and passion for abstract thinking. And this drew me to fundamental problems, and it also drew me to theory. And I mentioned to you earlier that I had worked on a theoretical master thesis, then I switched to an experimental PhD thesis, and then eventually, after my PhD and first postdoc, I went into hardcore applications, combustion research. So while I worked on combustion research and worked on applied research, I learned a lot about myself. I saw, on the one hand, the deep satisfaction to work on problems which are so self-evident somebody has to work on it. If you work on clean combustions using laser light, you can talk to all your friends, you can talk to your parents, and everybody understands what you are doing. It's so easy to explain why it is important to use modern technology and laser technology to make combustion cleaner.
It's a little harder to talk about Bose-Einstein.
If I now tell people that there is this tiny little amount of gas, it's smaller than a millimeter, but it's terribly cold and it's terribly exciting to study the properties, I'm not sure if everybody understands me. So I think you get the point.
Yeah.
So I felt the satisfaction to work on applied problems. I also felt I was in the middle of life. I talked to engineers at an at the Volkswagen company, because we had a collaboration with Volkswagen and even used our laser equipment there on a test stand to look at a diesel engine at Volkswagen. So I felt I was really relating to real life problems with real life people and diversity and all that. But I was missing something. I was somehow missing the long-term challenge. I was working on problems and solving problems, but I felt the desire to work on problems where you don't even know if there's a solution. So I really felt, while I did this applied research, I want to work on something else. There was also one other thing I learned. I felt that applied research was more directly contributing to the solution of problems I identified with. But while I did the applied research, I also realized how much applied research draws from fundamental research. For instance, my training in fundamental spectroscopy enabled me to do applied research with a different approach than the people who had done applied research all their life. So while I did applied research, I always maybe felt more that we have a certain division of labor between people who do fundamental research and people who eventually take care of applications. And so after realizing that, after also realizing my talent and my desire to do fundamental research, I then decided I'm changing my career again. I want to work on fundamental problems in physics. So this was a big step, and it had a lot to do with finding out something about myself, my own motivation, and in some sense, I really found out what I wanted.
We associate lasers in the popular world with heat, not cooling.
That's true.
How did you suspect that a laser would be a cooling device at extreme low temperatures that you wanted to explore?
Laser cooling is pretty cool. Laser cooling is an amazing phenomenon, and it attracted a lot of attention when it was developed in the 80s. So when I was about to make a decision again, I wanted to work on something fundamental. How did I pick my area? Well, I felt at that point, I was around 32 years old, I couldn't start completely over again. So I wanted to work in a fundamental area of physics where I could continue to use some of my tools, namely lasers, optics and spectroscopy. And so I talked to many people, I looked through proceedings of conferences, and what I identified as the most promising and most exciting area was laser cooling. So laser cooling was already developed quite well at that point, but I felt there was a big potential to study the properties of laser-cooled atoms and explore, other science with cold atoms. So I decided that is the most exciting field I can contribute to with my tools in fundamental physics. And so what I did is I sent letters to some of the best groups all over the world and asked if they would offer me a postdoctoral position. And eventually Dave Pritchard here at MIT offered me such a position, and that led to the fact that eventually in early 1990 I arrived at MIT. Now, I haven't really addressed your question about why lasers cool and when do lasers cool and when do lasers heat.
I noticed that, yes.
So
you haven't addressed that.
Let me do that now.
Please.
So lasers are, of course, a directed form of energy. If you hold your hand in a laser beam, you feel the heat. Because the light, the photons, which is energy, are absorbed by your skin, are converted into random motion, and we feel that as heat. Well, with some of the lasers we have in our labs, you can even burn your flesh. So this is how lasers heat. But if you apply laser radiation to atoms, there's one important difference. The atoms cannot keep the light. When atoms have been excited to more highly lying, more energetically higher state, they have to re-emit the photon. So a photon which is absorbed with 100% probability is re-emitted. So therefore the energy which the atoms absorb is emitted again as fluorescence.
But that's a straight-ahead trade.
So that would be a straight-ahead trade. And now, on a much more subtle scale, when we use the right laser light with the right frequency, we can arrange for situations where the emitted light is slightly more energetic than the absorbed light.
And so that means as you apply the laser to the atom and the atom continues to re-emit, it loses energy over
Exactly.
time.
And it's quite fascinating how that comes about. So what happens is we need a frequency shift of the light, but in its simplest form, this is just provided by the well-known Doppler effect, which makes the frequency of light depend. If a moving object emits light, the frequency depends on the direction of emission, and that is sufficient to make lasers cool.
When did you... I mean, you say that laser cooling was fairly well known at the time that you came to MIT. What potential did you want to explore using this tool as you understood it to be so exciting?
Well, I think I was drawn to the field by its novelty and general potential, also by the possibility of analyzing and exploring properties of cold atomic matter. Cold atoms can form cold molecules. That was quite exciting, and that was actually the project I was hired for by Professor Dave Pritchett.
And the mission would be to explore matter at states of extremely low energy in a whole variety of settings.
Yeah, I think that was the fascination. And I felt I had certain, questions about the wave nature of atoms. I was intrigued, but as far as I remember, I wasn't really focusing on one specific thing. I just felt it was really cool, a cool area to work in. But let me give you my assessment, which is, I think, interesting. In 1989, I thought that laser cooling had gone through extremely exciting times. Sort of between the early 80s and late 80s, new technologies, surprising cooling technologies were developed, and it all came together. It all came together that one could cool, manipulate, and trap atoms. And my assessment was actually that the field had sort of reached a certain peak, and I was expecting that now the field would be at a very high plateau for at least some years to come. And this is where I wanted to contribute. Of course, ideally as a scientist, you want to contribute to a field when all the pioneering work is done. And, well, I didn't see, such a field or such an area within my reach, giving the tools and my education. So I felt laser cooling was the best I could do, but I really had the impression that laser cooling had reached sort of its peak, and now there was a long plateau for several years. And in some sense, I was right, because when the Nobel Prize was given for laser cooling, it was given to the people who contributed to the development of those cooling techniques in the mid and late 80s. But what I couldn't know at this point is that when laser cooling was combined with evaporative cooling, that the whole field would jump up to another level which was completely off scale. So at that point, the best of laser cooling, the very best of laser cooling, was still to come.
And the combination with evaporative cooling, which is another technique, when did that come into being or occurred to you and your team as a tool?
Well, being at MIT, you are, of course, familiar with evaporative cooling. Evaporative cooling was pioneered by Professors Kretek and Kleppner at MIT. And, of course, being at MIT, I knew about it.
Now, evaporative cooling, I think of that, and I think of the very lay, traditional notion of how an air conditioner works, where the energy from evaporation is removed from a space, and by doing that continually, you can cool air or cool a room.
Sure, sure.
But on the scale that you're talking about, it's very, very different. Can you explain?
Oh yeah, I was referring to the work of Dan Kleppner and Tom Gretek, who applied evaporative cooling to cold hydrogen atoms in an atom trap. So I was more talking about how can you cool atomic samples, and to find, and this was really pioneering work, to apply evaporative cooling to kind of this whole new system in a whole new range of temperature.
And basically, you're taking the high energy atoms relative to the system and bumping them out of the picture so that the average energy goes down, down, down.
It's as easy as that.
Yeah, easy for you to say. But on an atomic scale, how do you identify the hot atoms and kick them out of the system without adding more energy?
Well, that can be done in two ways. One is we keep the atoms in a trapping potential. So the atoms are like in a, you can think of it as marbles in a cereal bowl, and they move randomly around. And by lowering the rim of the bowl, you allow the most energetic ones to jump over the rim. It's very
That's
easy.
good.
Another method is to use radio frequency or microwave spectroscopy, but it's actually a variant of that scheme.
And by combining this with laser cooling, the low temperature potential you could see was what?
So that's now an interesting question, because now we are talking about the early 90s. So what happened is, with laser cooling and evaporative cooling, the cooling techniques both were well known, and there was some speculation that maybe those two powerful cooling techniques could be combined, but the general opinion was that it will not be possible, because laser cooling only works at low density, where the laser light is not absorbed by the atoms, and evaporative cooling only works at high density, because the atoms have to collide and stay in thermal equilibrium. So it seems, and that's what many people said, that there was a big gap between the highest density you could reach with laser cooling and the lowest density at which evaporative cooling would set in.
So did you set about to bridge that gap, or?
When I was a postdoc with Dave Pritchard, we bridged the gap. And it was sort of interesting how it happened. Namely that, and I think it was just the ideal combination of somebody who joins as a postdoc from a different field and somebody who has all the experience like Dave Pritchard. I know as a postdoc, I have to sort of learn, kind of read all the papers in a very short time, because I have to come up to speed very quickly. I can't go through kind of a year of preparation like graduate students do. As a postdoc, you have to learn how to learn, and you should learn rapidly. So I was reading all the papers and asking questions and having my own thoughts. And I know that I had discussions with Dave Pritchard and said, why wouldn't evaporative cooling work? Why not? And he referred me to some papers. I analyzed the papers and said, but shouldn't there be a window? And we started talking about it. And our conclusion was that there was a gap to be bridged, but the gap was not very large. And ultimately, we were building on a machine. Dave Pritchard had a grant with work for proposal to study formation of molecules out of atoms, and we sort of were building an experiment along those lines. But we kept on discussing, how can we bridge the gap? How can we do one more improvement to laser cooling, which would then hopefully jumpstart evaporative cooling?
How did you acquire lab space to investigate these ideas?
Dave Pritchard had labs. I was working in his labs.
But is it unusual for a postdoc to come in and suddenly get lab space?
No, I was sort of pretty much put on an experiment which was started by Dave Pritchard. He had an earlier postdoc who had worked on that, and I took over. What was unusual is that the experiment at that stage was sort of, the concepts were not fully worked out, so it was an experiment which was just being put together, and there was an opportunity to come up with own ideas and your own concepts.
But in any institution, there's a limited amount of lab resources, and it seems that a lot of your colleagues were as excited by your investigations as you were and voluntarily gave up lab opportunities so that you could have them.
That actually came later after I was appointed as an assistant professor. But we are just talking about the postdoc time when the opportunity arose to bridge the gap between laser cooling and evaporative cooling.
All right, well, let's talk about the postdoc moment
Yeah.
then before we get to the assistant professorship. When did you know you would bridge the gap?
Well, that's a moment I will never forget. I was 2 years into my postdoc, and we were laser cooling atoms, and we used this new idea which myself and Dave Pritchard has come up with. And what we saw was completely pitch black clouds which just absorbed all the light completely which we are sending at them because they were so dense. So we had reached higher density in large clouds than anybody had ever reached before. And very soon it became clear that this could bridge the gap.
What element were you using?
It was the element sodium. That was actually, sodium used to be the workhorse of atomic physics in the 70s and 80s. And Dave Pritchard has worked with sodium for most of his scientific life. And that was our natural choice for laser cooling. And what then happened was also a formative moment. We started then to discuss what can we do next. And it wasn't first very clear. Dave Pritchard had worked out all these ideas about how to form cold molecules from cold atoms, and he felt this higher density would just be a boost to it, and he thought we should continue along those lines. And myself, as a postdoc, I said, well, why don't we go for the holy grail? Let's combine laser cooling and evaporative cooling. There is a chance that it will work. And for maybe, I don't know how long it was, for a few meetings we discussed it back and forth. And also the graduate students who worked with me, they were ambitious. They wanted to go for kind of the big challenge. And I will never forget that after a few such discussions, Dave Pritchard just said, I let you do what you want. So Dave Pritchard had really the greatness of abandoning his own ideas. Some other people got famous with these photo association, putting cold atoms, associating cold atoms into molecules. But he allowed me as a postdoc to, go for this combination of laser cooling and evaporative cooling, which some people regarded as sort of uncertain. I know in 1995, a few months before Bose-Einstein condensation happened, I got reviews on my proposal where people felt that there was, such a long way to Bose-Einstein condensation will probably never happen and things like this. So it wasn't clear that this was a golden road. But Dave Pritchard was a great person, and he also felt that I was so enthusiastic about it, he wanted me to try it out.
And it's fair to say that that was a moment of extraordinary generosity in your career.
Number one. And number two is, it was also a moment of really change. We had this new technique called the dark spontaneous optical trap, where we had reached higher densities than people before. But before even writing and submitting the paper, we ordered a list of critical pieces of equipment in order to go for evaporative cooling. So there was really this sudden moment where kind of all your thinking, all the resources of the lab, whether it's student or equipment money, everything became suddenly focused on a new goal.
So you made the big bet on your question, and all the resources were devoted towards figuring out if there was an answer.
Yeah.
An exciting but scary moment.
Well, I felt it was exciting. I wasn't scared at this point.
Yeah, you don't get scared. But that much scares you. So what was the target then? And explain that perhaps at the end of that pathway of low energy lay Bose-Einstein condensate.
Well, I tried to be reasonable and conservative. I knew about Bose-Einstein condensation, but it was also clear that with laser cooling, we were missing a factor of million in density, or in phase-space density, which is a more technical term. So we were a factor of 1,000,000 away from Bose-Einstein condensation. And I felt it was almost frivolous to talk about it. We are now going for Bose-Einstein condensation. So for myself and for my lab, we declared the goal: we want to combine laser cooling with evaporative cooling, and we want to get at least a little bit colder and a little bit denser than anybody before us. We knew that ultimately this could lead to Bose-Einstein condensation, but we felt we were far away from it.
Well, let's describe what the condensate actually means. At a certain density and at a certain low energy, the atoms would do what?
The atoms would fall into lockstep. Instead of moving randomly, they would all march in lockstep, literally, which means they would form one big coherent wave, a giant matter wave.
And this matter wave, does it merge quantum events and other events in a way that you can't see anywhere else in the world? What is it about that matter wave that is fundamental?
Well, a coherent matter wave is for atoms what the laser is for light. If you have light from a light bulb, the light is emitted randomly in all directions. There are little waves going everywhere, and the laser light is just one coherent wave. And similarly, in an ordinary gas, atoms move randomly, and in a Bose-Einstein condensate, they march in lockstep. So it's not that the atoms are merged, it's just that all the atoms do the same thing, exactly as the photons in a laser, they all do the same thing. They're not moving in random directions, they're just in a single mode of the electromagnetic field.
Does that constitute a different state of matter? A new state?
It is a different state of matter, which is very, very different from ordinary states of matter. However, I would actually adopt the suggestion made by Fritz London in the middle of the 20th century or so, that we should use the fifth state of matter for systems which are quantum mechanically, which show a macroscopic coherent state. And this class of matter would include the superconductors and the superfluid, and the Bose-Einstein condensate would be another member of this very distinguished class of quantum matter. Some people have sort of labeled the Bose-Einstein condensate of a completely new state of matter. I would disagree. I think
you would say it's part of a class.
The Bose-Einstein condensate has a lot in common with superconductors and superfluids, but this is a very special club of systems, and the Bose-Einstein condensate is now the first gas, and the fact that it's a gas makes it distinctly different, but still I would categorize it with these other examples.
Can you describe the experiment and the sort of time frame of the project that actually delivered that result? Getting the atoms to be of a sufficient density that they constituted this Bose-Einstein condensate state?
Yep. So we've talked about the combination of laser cooling and evaporative cooling, and in 1992 we bought some vacuum equipment, electric equipment, optical equipment, and put it together. And
that was fun, right?
That was a lot of fun. But what I had never expected was that only a few small ideas were needed to take the system to Bose-Einstein condensation. We were talking about 6 orders of magnitudes, a factor of 1,000,000. And it was almost like we took it in one step. I expected that every time we get a little bit colder, we find something new, something unknown. We have to learn something about it and implement something new. But it really happened that there was only one modification to the atom trap we had to implement, but other than that, we could really jump over those 6 orders of magnitude with one big jump. It was really dramatic.
That is dramatic.
So we got the machine to work. There was one major modification we had to do just to build a sort of a leak-tight trap, a trap where atoms couldn't leak out.
A magnetic trap?
It was a magnetic trap. Well, we used a combination of optical magnetic trap, but eventually there was a leak in the trap. We had to plug it, but after that, Bose-Einstein condensation just happened.
And you saw it how?
Well, we looked at the atoms by, now I would say, digital photography. You can image a cloud of atoms by illuminating them with light and then casting the shadow on a camera. And the shadow told us how the atoms were moving. And in a normal cloud, atoms, if they're no longer in a trap, just move away from each other because they have random velocity. But if the cloud is very cold or it's a Bose-Einstein condensate, the velocity, the thermal motion is so slow that the cloud is hardly expanding at all. So it was a little bit like that. If you drop a normal cloud, it just expands. If you drop a Bose-Einstein condensate, it drops like a rock. And that's what we saw.
Do you recall what you said to your colleagues when you observed that result? What did Pritchard say?
Well, everybody was delighted. I remember the moment we saw it in the lab, which was full of tension and anxiety. Well, the situation was slightly more complicated because for over several years, actually for probably about 3 years or so before Bose-Einstein condensation happened, my group was in a head-to-head race with my colleagues at Boulder. And the group in Boulder had actually, in the summer of '95, pushed ahead of us. They had actually observed Bose-Einstein condensation in June of 1995.
And you were using different elements, right?
We used the different elements, we used different methods, we used a different trap. But in both cases, it was about the combination of laser cooling and evaporative cooling. So when we discovered Bose-Einstein condensation in sodium, that was in September, so 3 or 4 months later, I think the first reaction was big relief, because we realized that Bose-Einstein condensation would start a new era in atomic physics. And we were, of course, afraid that with our atom and our techniques, we may have bet on the wrong horse. And so we were pioneers of the field. I had put all the resources into the pursuit of Bose-Einstein condensation, and we came very close. But there were a few moments where we were afraid of missing out on all the excitement. So when Bose-Einstein condensation finally happened, it was probably more, the immediate reaction was the big sigh of relief rather than the excitement for new discovery, because the first observation had been made a few months earlier.
Then how did you extend on your relief and get into an area that was fundamentally new? I guess I'm speaking of the expanding or contracting clouds that begin to tell you a little bit about how the atoms behave.
Well, in hindsight, in 1995, after we had observed Bose-Einstein condensation in sodium here at MIT, we made the right decision for the wrong reason. And that was, in these moments of anxiety where we didn't know whether our method would work, I was sort of feverishly analyzing everything I know. I mean, I felt in the tightest competitive situation. There was sort of an exciting time ahead. I was well positioned with my group, but I had to make the right decision. I had to steer the group into the right direction. And I thought very hard about, which used to be a bottleneck in the experiment, namely the magnetic trap. And I came up with a new design for magnetic trap. And even before we observed Bose-Einstein condensation, I diverted the effort of the lab and had people work on the new magnetic trap. And the moment when we observed Bose-Einstein condensation, the new design was sufficiently well advanced that we took the risk and said, we are not even studying the Bose-Einstein condensation. We had observed it. We had only seen it on 2 nights. And we had written this important paper on our observation of Bose-Einstein condensation, which was crucial for the Nobel Prize. But only after 2 nights, we took the whole machine apart and implemented the new idea. And when I said it was the right decision for the wrong reason, my analysis was at that point that there were so many groups in atomic physics who were immediately jumping at it. And I knew those people were jumping at it with more resources, with more experience, with, all the established groups. And I felt that our setup needed an improvement just to be competitive. And I also thought that we would put in the improvement in a few months. What happened is, for 6 months, we couldn't produce Bose-Einstein condensation. The machine was down, we lost the vacuum and all that. But 6 months later, we had a setup which was controlled, 10 times more atoms, which was robust. We had a dream of an experiment. And what had happened is, the competition hadn't built that. All the labs were struggling to learn about how to combine laser cooling and evaporative cooling. They had to learn what my group and the Boulder group had developed over 2 years, and it took all the groups, even with abundant resources, with postdocs and experienced people, it took all the groups 2 full years before they could repeat Bose-Einstein condensation. So now, for those 2 years, my group and the group in Boulder had the only working machines to produce and study Bose-Einstein condensates.
And your machine was better.
And my machine was just so much better. We had 1,000 times more signal than the Boulder people. We had a better trap. We could just, study the condensate, do one experiment after the other. So that was an amazing time. It's a dream of a scientist. You have the stuff which everybody tries to get and nobody gets it, and you have it. And you can just study it, look at it, have ideas what to do next. It's almost, it was a gold rush.
When you say right decision for the wrong reasons, it sounds like you're saying that that is the position that every scientist wants to be in, finding yourself with the machine and the ability ahead of everyone else. That's a great thing, but that the competitive motivations and the worry about being upstaged by your colleagues is maybe one of the unfortunate things in experimental science that you wish wasn't there.
No, absolutely not. First of all...
So what was the wrong reason?
Well, I was in an advanced position. I had one of the 2 machines in the world which could produce a Bose-Einstein condensate. And I think most reasonable scientists, if they have reached a stage where they can do unique experiments, they wouldn't take the machine apart. But we took it apart and improved it by a big margin. And the reason was that I underestimated what we had accomplished. I underestimated the uniqueness of our accomplishment and felt other groups could soon follow up and would have improved setups.
And your worry was misplaced.
So my worry was misplaced. But on the other hand, I think competition brings the best out of us. And especially in our field, it's friendly competition. It's competition where your competitors acknowledge what you have done, where people are excited about real good science, even if it hasn't happened in your own lab. And this is really competition which brings the best out of you. I think without competition, I would not have kind of thought so hard about what is the best solution. And we probably worked even harder because we knew there was competition.
You've talked repeatedly about wanting to do things that are rooted in real-world problems and to find results that have the potential of helping real-world people. How does this experiment satisfy that in any way?
Well, to some extent, I have detached myself from the goal by a time scale which is maybe 20, 30, 40 years. I think the work I'm doing right now is fundamental. It improves our understanding of matter. it leads, in conjunction with theoretical colleagues, to an improved description of matter. But right now, the matter which we use as a test object to observe and understand new phenomena is sort of so cold and you can say so special that it cannot be used for anything applied. On the other hand, a better understanding of materials should lead to novel materials and novel devices in the future.
Do you think there are applications of these extreme low energy states for the development of super conductors and materials which will make energy use more efficient?
That's the hope. The hope is that cold atoms may provide critical insight for future development of superconductors.
I've heard described that some of the behavior of matter that you've observed at low energy is remarkably similar to the apparent behavior of matter at extremely high energies in things like plasmas or inside of a neutron star. Do you buy that, or do you think that that's an oversimplification?
That's not an oversimplification, because we work at extremely low density, and what happens at low temperature, very, very low temperature, at very low density, can be equivalent, if not identical, what happens at higher temperature and higher density. So the scaling is completely sound, and in neutron stars, for instance, you have much higher temperatures but also much, much higher densities, and you may encounter physics which may be similar or exactly the same as we study in our laboratories.
Is it possible to understand the nature of the interior of a neutron star billions of light years away by observing the atoms on your desk?
No, it's not possible, but it is possible to contribute one piece of understanding. For instance, when you want to figure out if you have extremely cold neutrons and they strongly interact, what is their energy? We can simulate that with cold atoms. But there are, of course, many other properties of neutrons, many special properties and the environment of the neutron star which we cannot simulate. But a question like that, what would be the base energy for a neutron star at zero temperature? We may find the answer with cold atoms.
That's a result that you might not have expected to come out of this journey that you began in the middle of the 90s or early 90s.
You're absolutely right. If I think back about the year I described in 95 and 96 when we were brainstorming what are the new experiments we can do with Bose-Einstein condensates, we had some good ideas, but even our boldest imagination was not sufficient to anticipate the developments which the field has taken in the following years.
So there was no plateau?
No. It was just shooting up, and some people feel the field is still expanding.
When you became an assistant professor, what explains the generosity with which your colleagues appeared to donate, voluntarily give up lab space to allow you to explore the questions that you were working on?
Well, the support and mentorship I had as a young scientist and as a young professor here at MIT was really almost unprecedented for me. So, there is the issue of lab space, but what came even earlier was the generosity of my mentor and postdoctoral advisor, Dave Pritchard. Dave Pritchard has been a pioneer in laser cooling, and in collaboration with me as a postdoc, things were even pushed further. So Dave Pritchard at this point had 3 experiments in 3 different subfields of atomic physics, and it was probably clear at this moment, but definitely clear in hindsight, that the laser cooling experiment was his most promising and best experiment. And when there was a possibility that I would join the faculty as an assistant professor, he told me that, well, he didn't want to create a shadow problem, that I would do laser cooling in his shadow. And he told me if I were to stay at MIT, he would get out of laser cooling and hand me over all the experimental resources. This is a highly unusual offer, almost unheard of, that a creative, active scientist is giving up is getting out of the field he has helped to create, is handing over his best experiment, his best lab to a young assistant professor. And at the same time he told me, but this is your own experiment, we will not publish papers together. You can ask me for advice, but I want to make sure that you have your full independence.
Can you imagine you yourself doing the same for some young assistant
In
professor?
some way, I've just done it. I handed over one of my labs to Martin Zwirlein, who is a young assistant professor and one of our young stars. But coming back to 1993, when Dave Pritchard made me this offer, it was hard for me I felt hard to accept it. He was this famous person, and with what expectation would I take over this experiment? I wasn't sure whether I would really succeed and whether I could, earn this enormous trust and credit which was given to me.
Well, he knew one thing about you. Pressure works with you.
Well, and I know there was one of these still memorable discussions. I sat down with him and told Dave all about my uncertainty whether I would succeed or not. I told him that I'm here with, children and a German wife. I can't even say for sure whether I will stay forever at MIT or in this country. And Dave just said, I know all about that, and all I expect from you to work hard and continue what you have done. So he took all the pressure off my shoulders and just said, well, just go with it.
Focus on science.
And
do what you do best.
And what happened is almost history. 2 years later, my group had realized Bose-Einstein condensation. If I had started at any other university, I would not have been able to build up a lab in 2 years. So after 2 years, my group contributed to one of the most exciting developments in physics, and we were right in the middle. So what I did at that point, I had actually thought Bose-Einstein condensation could motivate me for my whole lifetime. I would get colder and colder and study this and that this is sort of the big goal which keeps you focused on good science for years and decades. But after 2 years, I was there. So I went actually to Dave Pritchard and said to him, I would not have done it without you. I was to some extent executing ideas we had developed together. I was taking over the lab from you. I want you to co-author the paper. It's one of the most highly cited papers in physics. And Dave said, after thinking about it for a moment, he said, no, I want you to take the full credit.
So, finish the story with Dave.
So I still feel that what Dave Pritchard has done for me, how he has supported me and mentored me, was highly unusual. And there were moments it was just difficult for me to even understand it. So let me try to use the words which Dave Pritchard used to explain his magnanimous behavior. At some point he said, well, I gave up an experiment, but I got a wonderful colleague at MIT. At another time he said, well, and which I think it's just wonderful expressing kind of the feelings. He said, well, he said it in a speech. He said, I gave Wolfgang the keys to the family car because he could drive it faster than I could. So family car, sort of the two of us being, a couple for so many years, collaborating on various levels, has really been a wonderful experience.
Is that a value that permeates MIT in your experience?
The value of enjoying science and being excited and using that as one of the, one of the most important motivations, I think, is true. I think the special circumstances of supporting somebody are really unusual. I think the atomic physics group at MIT has, with Professor Kleppner, Pritchard, has sort of this wonderful tradition and history, and it's a very, very friendly family.
Describe your relationship with Professor Kleppner.
There was first, sorry, just two more things I want to say.
Yeah,
We're done in a few minutes, but about Professor Pritchard. So that's how it developed, and what was very satisfying for me after I was established and became as famous as Dave Pritchard, or to some extent even more famous, the two of us could collaborate again. So Dave Pritchard told me we won't publish papers together because he wanted me to get fully independent, but then as two independent people, we have now worked together, jointly supervised students for about a decade. And in a way, what I also find remarkable is that initially, he, of course, had pioneered the field. He taught me many things. He mentored me. But right now, Dave Pritchard is very focused on educational science, so he doesn't really have the capacity to, run a lab completely by himself. But in collaboration with me, he can still do wonderful physics. So it's for me almost like a life cycle of the two of us have always been a team. A team when I was a postdoc, a team when we were independent, but had independent research groups, but there was a lot of advice and camaraderie, and now we are collaborators again. It's just those life cycles. And one way how I was able to express what Dave had done to me was when we came back from the ceremony in Stockholm. We were back at MIT. I went to his office and gave him the original of the Nobel medal. I told him I couldn't share the honor of the Nobel Prize with him, but that he has been a big part of it, and this is how I want to express it. And I know it meant a lot to him.
What was it like to get the call?
Well,
that bad, huh?
No, it's a crazy moment. It's sort of a moment where you're called up at 5 o'clock in the morning, so your brain is not fully working. And you hear somebody telling you that you just wake up, get to the phone, and somebody tells you that he's from the Swedish Academy of Sciences, and they want to tell me that I've been awarded the Nobel Prize in this year. So, you react with joy, with pride for MIT, for your collaborators, for yourself. It's a wonderful acknowledgement, and it's very, very special. It's sort of great. You're struck by it. You're hit by it.
How did the family react here at the Center for Atomic Physics?
Well, it's just over-joyful. It's just a celebration, a pride, a sharing. It really brings together the whole community. It also brought together the whole field, because for Bose-Einstein condensation, the Nobel Prize was given only 6 years after the discovery, and the field was in full swing. So everybody who was working in the field felt elated, because the whole field became distinguished as one of the important frontiers of physics.
That's great.
You ask about my relation with Dan Kleppner.
Yes.
Well, let me fill in. Dan Kleppner was the PhD advisor of Dave Pritchard, and I felt to some extent the way how Dan Kleppner was educating and Dave and nurturing his career and allowing him to become independent and famous, that this sort of repeated itself between Dave and myself. Now Dan is sort of the senior member of the atomic physics group, and I've appreciated his, the science he's done. He has sort of enormous scientific skills. He has shown great taste through his career. He has worked on many important frontiers. But he also has this wonderful, balanced personality. And when I was an assistant professor and I felt I was in competition and just needed his advice, he always gave advice. So his balanced personality and his friendship and his calmness were very, very important. I felt as a young assistant professor, I had this dynamic environment at MIT with all these wonderful students, but with my two mentors, Dave and Dan, I also had the experience, the tradition and the wisdom. And I felt when I was a professor, but there were situations I just didn't know what to do. I needed a sounding board, and I always found it.
And is that something you're passing along to your colleague Martin Zwerlein, a young physicist who's somewhat in the position that you were nearly 20 years ago?
I hope so. At least I'm trying. I'm not sure if I have the same balance and wisdom as Dan Kleppner, but I'm trying to give him good advice whenever I can.
And what's the excitement that he brings to the department that you see in his work that maybe reminds you of experiences in the past?
Well, Martin is just a bundle of energy and joy. He can be excited about physics, he's understanding physics, he conveys physics. You just realize that everybody who's working with him is pulled along by him, or even more positively, he brings the best out of people. But you really realize that after he came back to MIT and started his own lab, the sort of level of liveliness and energy and excitement in our hallway has increased.
Does that mean different music being played on the CD players in the hallways, in addition to the great physics?
If you want to use it as a metaphor, yes, it's sort of like an additional dance with a lot of intensity. I think intensity is also a good word. He brings sort of intensity to it. And that's also what MIT is about. MIT is a high-intensity place.
How important is teaching and interacting with students in your experience here, in addition to being able to have access to fundamental research?
I love to teach. Even if somebody would offer me to opt out of teaching, I would not take this offer. I want to teach because it keeps me grounded, it keeps me connected to the basics, but also it forces me to again and again present the logical structure of physics and the basics of physics to learning students.
And what groups of students do you teach at this point? All graduates?
I actually alternate between undergraduate and graduate students. So the past semester I was a recitation instructor in quantum physics for undergraduate students, for juniors, and in the spring semester I will be teaching the graduate course in atomic physics.
And for undergraduates, what can you convey to them that sort of maybe reminds you of yourself or is important about teaching when you're presenting to them material that's well worked out in your mind, but is a discovery in their mind?
I think it is this deep understanding. When I teach, I think it is even more important than teaching the material to convey your own personality, to convey your personality as a working physicist. I think what young people need are role models, people they can identify with in terms of the passion they have for their subject, or the intensity, or the way they think, the way they analyze. That's, I think, what young people have to learn. So when I'm in the classroom, I sometimes like if a question puts me on the spot, I may not know the answer, but I have to derive it. I'm struggling, I'm reiterating, but I show my thought process to the students, tell them what I check out, how I maybe construct the answer of something I know, and then add something I have to think about it. I think to present yourself as a working physicist to the physics student is important.
And to convey that Legos are important over the long haul.
Yes. I think what I think showcase here for MIT is this kind of mentorship. I mean, there is something about, I know that in the physics department, we rarely hire senior people. We want to, nurture ourselves, young talent. So almost all the hires in our department are done at the assistant professorship. So we want to identify talent early on and then nurture and develop it. And a lot of the people have become, well, the stars in their fields. And also many of them have stayed at MIT for many more years or for their whole lifetime. So this focus on young people and introduce young people or bring in young people to MIT and make sure they succeed, this is really an MIT tradition. I may have experienced that in an even more unusual form, that Dave Pritchard was stepping back, was handing me over the experiment. But in a way, what I experienced in that form really reflects on the culture which we have in the physics department.
Oh, that's great. Well said.
I don't know how much it really applies to all the departments. I don't know the hiring kind of policies of other departments.
Well, I mean, I think this mentorship idea is a consistent theme throughout all the interviews that we've done across many disciplines at the Institute. So it's not, I don't think we've necessarily heard as dramatic a story.
There's maybe one element which also fits into tradition and mentorship, and that is when I received the Nobel Prize, I shared it with two of my colleagues and competitors in Boulder, Eric Cornell and Carl Wyman. But it's interesting that Eric Cornell was a graduate student of Dave Pritchard. He left shortly before I arrived. And Carl Wyman was an undergraduate student with Dan Kleppner.
Well, there you go.
So it's clear that and there are other very famous people in the field who have really been educated by Dan or by Dave.
It's all in the family.
So Dan or Dave have really created a family of atomic physicists, and their impact on the field cannot be overestimated.